Now we come to the third method in nonlinear equation, which is Newton methods. Okay, Newton method is one of the most powerful and well-known numerical methods for solving root finding problems. So before this, for second and for bisection, we need two, right? Initial approximation, but for Newton, we only need one, P0, one only. But it must be near the root. If it's too far from the root, maybe it will not converge towards the root. Okay, that's the problem. So the P0, although they only need only one P0, but it must be near the root. Okay. How Newton method works with only one initial approximation. Before this, we always use two, right? P0 and P1, A and B. We must have two. But how can we use only one to find the root? Newton method use tangent, the tangent to find the next P. Okay. See here, this is our P0, the starting one. This is given to us P0, and based from our P0 here, the tangent line will get us our P1. That is why we can use only one starting approximation value for Newton. If you can see, it is directly closer to our roots, so it can be much faster to find our root using Newton. As I mentioned before, the Newton method used the tangent line to find the next P, right? So P1 is the x-intercept of the tangent line to the graph f at P0, fp0. Okay? So, what is the formula of Newton method? Newton methods here need us to use the function of fp0 with the function f prime of the p0. This is one of the things that make it hard here to use the Newton method. We need to find f prime, and it is not given to us. Okay. Same as secant, the process can be repeated again and again to obtain P1, P2, and Pn, and then leads to convergence of P. The criteria also same as secant. We don't have interval like bisection, but we only have two here. Either one must be satisfied to stop the calculation. The Pn minus Pn minus 1 here must be less than our error, and our Fpn must be less than our error for us to stop the calculation and select the P. Example of the Newton method, how it works. So we have the first P0 given to us, right? And then the first tangent line here, this will be our P1 based from the calculation, right, of the tangent line. We will get our P1. Then based from our P1, the tangent line there, we will get our P2, and so on until we find close enough to our root. Next is the algorithm. Again, this class will only teach the manual way to calculate using this method. But if you want to make a program, you can apply this algorithm to your program to use the Newton method. Continuation step of the algorithm. Okay, now we come to the example. They ask us to use the Newton method to locate the zero of function fxx minus cos x. Use an initial guess of p0 equals to 0.5 and iterate until error 0.005. Okay, so we have error here and we have our p0. Remember, for Newton we only need one. The first thing we need to do is we need to find our f prime x. We need to find this first. How to find f prime x of x minus cos x? Okay, you need to recall back what you learned in your school, all right, in your previous calculus class. Okay, how to find the f prime. Okay, this will not be teach in this class. Okay, you need to refer back to previous class in your calculus and then you need to find how to find your f prime. For example, here the x for the prime will become 1, and for the cosine x, if you want to find the prime, it will become sine x. Okay, this is not from this class, this is from your previous study in your calculus, so you need to recall back on how to find f prime. Then if you already find this, I think from now on you can just use the equation to find the answer. After finishing finding your f prime, now is the time to use the equation. So find your fp0 and f prime p0. Okay, based on the calculation, we got your fp0 is negative 0.378 and f prime p0 is 1.479. So we already have our p0 here, so we insert the p0 and insert your fp0 and f prime p0 into the equation, so you will get your p1 value. Then you can check your p1 minus p0 whether it is less than 0.05 or not. In this case it is not, right? It is bigger, so the fp1 also we check, so it is 0.028, which is bigger. So based from these two, both are bigger than 0.05, our error, so we need to go for the next iteration. Next iteration, we calculate our fp1 and f prime p1, so we get your answer 0.028 for fp1, f prime is 1.686. We got our p1 already, just insert the value of those three and you will get your p2, which is 0.739. Then we check again both value, the p2 minus p1 and fp2, whether it is less than our error. Here 0.05. For the first one it is not. For the second one it is negative 0.001, so 0001, so it is less than our error, so we can stop at p2. We don't need to go for the next iteration. Same as the previous two method, I want you to make this table each time you do the Newton method here. So this is your p1, your p0 here, and then you calculate the fp0. Then based from that you calculate the f prime for your p0 here. Then you will get your p2. This is your p0 and then your p1. After your p1 you get the f for p1 and f prime for p1. Then you can get your p2. Okay, so in the p2 you calculate the fp2, sorry, you will get your 0.000 here. So this is less than your 0.005, our error. So we can say that the p 0.739, p2 here is equal to p, and based on our question 2 decimal points, so we can make the answer is 0.74 bracket 2 decimal points. Now we look at another example. Use the Newton method to locate the root for the equation here, and they give us our p0 here equals to 1 and iterate until 2 decimal point, which is the error 0.005. What is the first thing we need to do? We need to find the f prime. Okay, to find the f prime, again, this is not from this class, this is from your previous class in calculus, okay, in your school. Alright, so you need to know how to find the f prime. Okay, for the e here, you can negative e, alright, and for the x, it become 1. This is your f prime. Then after you find the f prime here, you can use this to find your p1 using the equation given. Okay, so we have our p0, fp0 and f prime p0, so this is the value here, so insert into the equation where this is your p0, this is fp0 and f prime p0, so we get your p1. So this is your p1. Then you check your p1 minus p0 here. whether it is less than 0.005, and then you can check again the FP1 whether it is less than 0.005. Unfortunately, for both 0.046 and 0.462 is more than 0.005, then you need to go for the next iteration. So our P1 is 0.538, so we need to find the FP1 and F prime P1. We already calculated F prime P1 before in the previous slides. So for F prime, just insert the P1 into the F prime equation here. And then we use the equation given for Newton. Again, this is your P1 here, right? So this is your FP1 and F prime P1. So you can get your P2, your answer for P2. Again, check for P2 minus P1 here, whether it is more or less. So it is more. Continue with the FP2. We check whether it is less or more. So we get the answer 0.0002, which is less than 0.005. So we can stop the calculation here. As you can see, compared to secant and bisection, using Newton, you can get the answer much faster, right? Usually 1, 2, maybe 3 iteration that you can already find the answer. You can already find less than our error. If you compare for secant and bisection, usually more than 3, 4, 5, 7 iteration. Okay. Again, the table is compulsory. You need to make the table easier for you to understand. Okay, this is your P0, right? And then you find your F and F prime, then P1, and then using your P1, F prime, and F, you get your P2, where you get 0.000, which is less than our error. Okay, so based on that, we can say that 0.567 here, P equals to P2, 0.567 is the answer. And of course, 2 decimal points, we make it 0.57, and with in bracket 2 decimal points. This is the answer that you need to make. Okay, this one is another exercise for you for Newton method. So we have 3 exercises for bisection, 1 for bisection, 1 for secant, and 1 for Newton. I hope you can discuss with your friends, and we will discuss together the answer on our next class. Okay, we also have Newton method with special function. Newton method can also be used to find a square root of a number. Let's say to find square root of 612, and this is the equivalent of finding solution of x squared equals to 612. The function to use in Newton method is fx equals to x squared minus 612. Okay, then you need to consider the fx, give you here the fx, and then the f prime. Alright, I think you know how to change the fx to f prime. So we give you this equation that can be simplified into this. Okay, I'll show you next how to use this example. For the example, they ask us to use the Newton method to locate the root 4. They give us the fx here equals to x power 2 minus 2. And they give us the initial guess. The x0 is 1 and the error is 0.005. So you know the given fx is x squared minus 2, so the f prime will be 2x. Then you substitute your fx and f prime to the standard formula given before. If you remember the previous 2 slides. Okay, this is the formula, the standard formula, and it can also be summarized like this. But if you do the calculation, it can be the same. If you put 1 into either this and this, the answer should be the same. So let's say the question here, they use the summarized version of the formula, and then they put the x0 into the equation, because you see here this formula is for x n plus 1 to find let's say you use x0, this is xn, right? xn. Okay, and then the xn, if you put into the equation 0, right? x0. So you will find for 0 plus 1, which means x1. So you can see here, this is the equation. N plus 1, our n is 0, so 1. And in the equation, it will be x0. So we have already our x0, which is 1. And then we have our x1 is equals to 1.5. After we get the value of x1, we substitute it into our fx. Then you will get 1.5 power of 2, and the answer will be 0.25. Then you need to check for convergence. What is the formula for convergence? Xn plus 1 minus x must be less than our error. Our error here before is 0.005. Xn plus 1 is what? This is your xn plus 1, right? Before you already count. Minus your x0 is 1. So of course it is bigger than your error 0.5. So it's bigger than, you need to continue. 1.5 minus 1, 0.5, bigger than error. So you need to continue. You need to continue. Use the iteration before in the previous slides, and then you do this table. Okay, where we can see directly your x0, x1, and your fx1, and then your next iteration where you have 1.5, then you will get your xn plus 1, which is x2 now. Okay, until xn plus 1 minus xn less than 0.005, then you can stop. So here you can see x3 minus x2 is 0.0025, which is less than our 0.05. Therefore the root for fx is your x3. Alright, you must remember how to get the final answer here. x3, which is 1.4142.